This is Chapter 1, Equations and Inequalities, Section 1.5, Solving Inequalities. Inequalities involve two expressions separated by one of the inequality symbols, less than, greater than, less than or equal to, or greater than or equal to. To solve an inequality means to find all the values of the variable for which the statement is true. And because of the inequality, this solution set involves a range of answers where formal notation is needed. So for this section, we're really just solving like we would solve an equation. The two differences are, one, how we show our solution, because now it's going to be a range of values, not just -4 and 3 or something like that. And so we'll have to write this in different ways, and we're going to look at some different ways to show our answer. And then there's one other thing to remember about inequalities that we'll get to. Other than that, these are pretty simple to do. So the definition of interval notation, it's an interval. We let A and B represent two real numbers, and A is less than B. So a closed interval would look like this. It's closed with a bracket from A, comma, to B, closed. And that's all real numbers x that are between A and B and could be equal to A or B. So the bracket means it could be equal to A, could be equal to B, and that's a closed interval. This would be a way a final answer might look, a solution set might look. An open interval, parentheses A, comma, B, consists of all real numbers x for which A is greater than greater than A, less than B, but cannot be equal to A or B. So that's called open, and we use parentheses. There are two half open, or you could say half closed, intervals, and they are the first one here where it's open on the A side and closed on the higher end. Remember, it's always low to high for an interval. A is always less than B in this notation. So it's not equal to A, but it could be equal to B and everything in between. Or here it shows it could be equal to A, so we're closed at A, but we're open at B. So that's what we call either half open or half closed, depending on your philosophy of life, I guess. Okay, in each definition, A is called the left endpoint and B is called the right endpoint of the interval. If an interval is unbounded, in other words, it just goes to positive infinity or possibly to negative infinity, then that's always an open interval. We never use a bracket with an infinity because that implies you get to a certain spot, a certain place on the number line, and you stop. And of course, we don't have, infinity's not a certain place on the number line where we could stop. Okay, so here are all the different possible solutions we may have. We've worked the inequality. We've done all the work to isolate the variable x, and we end up with something like this or any of these. So we need to look at how would we show that solution in set notation? How would we show it in interval notation, which is what we just investigated here? And then how would we sketch a graph of that? So let's go through each one of these. Set notation is very easy. It uses the curly brackets because that's what we call, indicates a set. So we have curly brackets saying the set of all x, and then this straight up and down line. It's not a slant line, it's straight up and down. And that means such that. I'm about to tell you what these x's look like. The set of x's, set of all x, such that x is greater than A but less than B. Notice I just took this and plunked it right in there. That's all you do. So every one of these is going to be like that. The set of all x such that. Put that in. We need the curly brackets because that says the set of. All right, in interval notation, well, we already saw what this looks like. This was an open interval, right? A to B, but not including A or B. Now to graph that, this is just a very basic graph. I just want to put a number line. I need an A, I need a B, and you may have done this previously in another course where you used open circles and closed circles, but we're going to use parentheses and brackets. So we'll put parentheses here and a parentheses here. Okay, so the parentheses is like your open circle and the brackets like your closed circle. And that's it. You don't need to put any other numbers. When we have numbers, you wouldn't need to put any other numbers. Okay, so we can get through this quickly. The set of all x such that x is less than or equal to b, greater than or equal to a. This is our closed interval, so we have brackets on each end, and in our graph, we have brackets on each end. Oh, what I didn't show, and I need to do, is we always want to shade where all the solutions lie. So here they are. I've shaded my solutions in both of those. Okay, the set of all x such that, here's one of those half open ones. X is greater than or equal to a, but less than b. So it could be a, and it goes all the way to b, but it doesn't quite get there. So on our number line, we have a bracket at a, we have a parentheses at b, and we shade everything in between. I'm kind of messing up with my shading there. There we go. Okay, the set of all x such that, now we're going to be open at a and closed at b. Open at a and closed at b. Open at a, closed at b, and everything in between. All right, sometimes, this is probably even more common that we'll see in our problems, we just get x is greater than or equal to some number, 17 or -5, whatever. So how do we show that? Well, continue with your set notation, very easy. The set of all x such that x is greater than or equal to a. Now how do we show it here? Well, it can be a or greater than. So it's closed at a, but it goes greater than. How far? Well, forever, never, never to positive infinity. And this said, infinity always involves an open interval. So x is a number greater than or equal to a. So on our number line, we find a, we put a bracket, and we shade everything, including the arrow that heads us to positive infinity. The set of all x such that x is just greater than a, but it's not, it can't be a, so it's open at a, and of course open at infinity. So we have a parentheses at a and everything greater than that. The set of all x such that x is less than or equal to a. All right, well now a is the highest this can be. The higher number's on the right, and it can be a, so it's closed. But where does it go to the left then? Well, it goes to negative infinity. And it's open always with infinities. So this shows that anything less than or equal to a. So here's my a, and we're going now to the left, all the way to negative infinity. The set of all x such that x is strictly less than a, so it's open at negative infinity and a. A, it almost gets to a, but never quite. Parentheses at a, shading everything less than. And then finally, what if it's all real numbers? Very rare. We probably won't see many like this because that's not all that interesting, but it would be the set of all x such that, and we can use some set notation. X is an element, kind of this funny looking E thing, element of, and this is how we notate real numbers in the set notation with 2 lines down for the R. X is a real number, it's an element of the real numbers, and how would you show every number on the number line using interval notation? You would say from negative infinity to positive infinity, right? And it would literally just be the whole number line shaded. Okay, that's how we'll show our answers, and now we'll work a few problems in the next video.